Greetings, this is the first video for the statistical mechanics. We're going to talk about microstates and macrostates of a binary system. The idea of binary system is that a choice is made out of two possible options and that each option is equally likely. This could be zeros and ones, lefts and rights, blues and greens, doesn't matter. In this particular example, we're going to have four people walk into a room or more, and each time they walk into the room, they're going to decide whether they're going to sit on the left-hand side or the right-hand side. N is the number of people who are going to make the decisions, and N sub R is the number who are going to end up sitting on the right-hand side. Okay, let's start with this particular worksheet. Hopefully you downloaded a copy. We will note that we will be using functions, procedures, plotting options out of two packages. One is the plots package, the other is the statistics package. As we found in class, the number of ways that we could find NR people out of N people sitting on the right is given by this formula. Fortunately, again, in Maple, a formula or a function looks very much like you would write it. The only difference is it has the colon equals. In our particular example, we're going to have, in this case, well, these will be molecules instead of people. There are going to be four of them. So let's begin by basically putting our icon there, hitting start, and then we jump down to the next execution group. We hit enter, and it gets executed. Then this one gets executed, and now we actually calculate the number of microstates in a macro state, in each macro state. So it's a sequence of doing this calculation from 0 to the number of molecules in the situation, and it looks something like that. Finally, we'd like to plot a histogram of it, and this looks like the following. So hopefully this makes sense. For 0 on the right, we get one possible way, one microstate, multiplicity is 1. For 1 on the right, we get 4. For 2 on the right, we get 6 possible microstates, etc. We can then add up all these macrostates, or actually the number of microstates in each macrostate, by using this next line. And it turns out to be 16. But you can see what we're doing is we're adding up the first one and the second one, the third one, and the fourth, even though this is labeled by number 0. Is this answer equal 2 to the n? We can ask that question, and it will check the equivalence of total number of states with 2 to the n. So now how do we calculate the probabilities? Well, the probabilities basically are, again, we're going to count from 1 to the number of microstates plus 1. The number of the state number, and then again the macrostate, the number in each macrostate divided by the total number of states. We will then take those probabilities and plot them, and when you do, you get something that looks like this. Maple has all sorts of features. I changed the labels. I made it kind of neat because you have N sub R. I changed the thickness. I changed the color. And then I have a way to make sure that I only view from 0 to 4 and up to some certain amount of, so it includes the whole thing. Okay? This is a 400 by 400 solution. When we define entropy, entropy is actually defined as KB times the natural log of the number of ways, of the number of microstates, or the multiplicity. So we literally define a function in terms of a previous function. And again, we can calculate all the entropies by going through and making a sequence from 0 to the number of molecules and calculating both the number of molecules, reporting both the number of molecules and the entropy. And eventually we will plot it. And when you do, you get a result that looks like this. So it looks very similar to the previous graph. But again, what we've done is we've taken the natural log of the number above. So that's why natural log of 0 is of 1 is 0, and we've multiplied by this constant known as the Boltzmann constant. All you need to do if you want to see a higher number is to scroll back up. Let's say we want to work with 8 molecules, 8 people, doesn't matter, and we want to produce all the same products. Instead of constantly hitting enter, 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 like this, okay, if I just keep hitting enter, 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 it will recalculate everything of that line, 256, number of probabilities, and now our entropy curve looks more like that. Not surprisingly, it's smoother because we have more molecules or people on the right. It's not too difficult to see what happens as our probability distribution is getting larger. To choose a very large number, instead of 8, let's choose 80, and let's hit enter. The number of calculate all the macrostates. Think about all the work you would have to do that. Create, there's our column graph. Notice now that it's getting more and more narrow. But look at the number of microstates. It's on the order of 10 to the 23. It's huge. We calculate the total number of microstates, and you can see it's a huge number. And it continues to be 2 to the number of molecules and number of people. And then when we calculate the probability, it looks like this. And again, as we've noticed, what's happening is the probability distribution is getting more and more narrow. At the same time, the top of the probability is actually decreasing. Hitting enter again and enter again, we get our probability our entropy plot. And again, our entropy plot it's a 0 entropy at the two ends. There's only one way, and the highest entropy is the one in the middle. If you want to change one more time, let's make it slightly larger. We'll choose 160, and instead of hitting enter, 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 I will hit this button, which is the triple exclamation point, and it will go through and recalculate everything at once. It's like running the program at once. And if you look, what happens is, again, the probability distribution is getting thinner and thinner, and it's actually, the top is getting lower, because there's so many other states. What do we conclude from this? As the number of particles or number of questions that have to be asked in the system, the likelihood that all the molecules end up on one side or the other side is astronomically small. They're all going to be close to the center.